Hello. We are going to look at a couple of different sections today, 1.1 and 2.1. So we're going to look first of all at inductive and deductive reasoning and then go into some set concepts. Now, the assignments are separate, but I'm only going to post the one video, so when we finish the 1.1, you might want to pause it and then do that homework and go back and watch it later. And it will say, I think, on the bottom of the slides which one it is. So let me share our content and we'll get going. Okay, if we're going to show a statement is false, we only need one counterexample, and that counterexample is underlined there. That's a vocabulary word. They will actually ask you sometimes to provide a counterexample, so it's important that you know what it is. And I think that teenagers and preteens are really geared into giving this counterexample, even though they don't even know it. But that means that you've probably had some practice yourself. When someone says, everybody is going, and mom says, you're not, she's done. She's provided one counterexample, so it's over. But this sort of thing can apply to something else also. So if you look at this and we say, everybody is going, you're not, well, any number times itself is even. Now we've moved into a math one, but you need to think of a number times itself that is not even. So you just have to kind of pause and think, well, how about 1 times 1? 1 times 1 is 1, and 1 is not considered an even number. 3 times 3, there's lots of them. So you just need 1, though, and then it's false. Adding the same number to a fraction's numerator and denominator does not change its value. Okay, so here I'm going to say, you're not. Any number times itself is even. 1 times 1 is equal to 1, and that is not even. Adding the same number to a fraction's numerator and denominator does not change its value. This is actually a very common misconception in middle school students. They think that if you take a number like 1/2 and then you add the same amount to the top and to the bottom, I like to do just examples with very, very simple numbers, then that one becomes 2/3. But 1/2 does not equal 2/3, and so this just simply doesn't work. Now with middle school, a lot of times you have to have them change it into fractions, decimals, so that they can see that 1/2 is 0.5, 2/3 is approximately 0.67. Now everyone loves math. Well, can we find a counterexample for that one? Do you know anybody that doesn't love math? I don't know, that one might be hard. Okay, so one thing that shows it's false is in a counterexample. Now, as we get into using reasoning, we have inductive and deductive reasoning. Inductive reasoning moves from specific examples to general conclusions. If you are using inductive reasoning, you're taking in the examples and observations, and then you are interpreting the general rule. I hope that we get to a point where this is not a good example, but I know when COVID-19 very first started off and all of the guidelines were very first coming out, people are supposed to wear masks, I texted my brother and said, apparently from observations, COVID-19 is shared through the chin, because that is where most people that I saw were wearing their masks. So you can take from that you can see where if you only use inductive reasoning, you can certainly get to a false conclusion. Now, I knew that wasn't the case then, but when you take in examples, those examples may not actually show you the rule of what is supposed to be happening. So here's just an example, and this one actually comes from the textbook that goes along with your course. And if you need to access that textbook and you don't know how, please just get in touch with me. I'm happy to let you know. Just send me an email, and I'll walk you through that. The last 6 times I went to the beach, traffic was terrible on Sunday, but not on Wednesday. So I'm going to conclude that beach traffic is worse on Sunday than on Wednesday. Now, that may very well be true because perhaps more people are traveling to the beach on the weekend. Inductive reasoning does not necessarily lead you to false conclusions, but it could. Okay? Deductive reasoning, on the other hand, moves from a rule, something that you've been told is supposed to happen, to how to apply it specifically. So on deductive reasoning, you are deciding how the rule applies to a specific case, and I've underlined D-E on that decide, just like I underlined I-N on interpret, because there's little things that can kind of help you remember which one is which. So deductive reasoning, if you pass a sign that reads road work ahead Monday through Friday, 6 a.m. to 6 p.m., and it's 3 p.m. on Thursday, then you should be able to conclude, well, there is road work ahead. You're applying it to your specific case. I know I taught high school for a number of years, and during those years I would tell students a lot of times in a high school, if you look around at the way the students are dressed and then you decide what the dress code is, you may be correct, but you may be wrong. It kind of picks on what determines whether or not you looked at examples from students following the dress code. On deductive reasoning, that is the person who reads the dress code and then decides whether or not they should or should not wear a particular thing. So inductive takes in the examples, and deductive decides how the rule applies. Now, we are going to be using these things particularly in math. So we use these types of reasonings. Right here, we're going to look at it, and we are going to use inductive reasoning, particularly when we take in examples of numbers in a list, or we take in the examples of shapes that are given, and they ask us to do something besides that. And sometimes you're asked to write instructions for something. So this is the sort of thing that you'll see on your homework problem. You've got a list of numbers, and then you're trying to determine what is next. So you go 3 to 12, 12 to 21, 21 to 30, 30 to 39. What is next? And so one of the things you can do is just figure out, well, are they adding the same thing? Are they multiplying by the same thing? So 3 times 4 is 12, but 12 times 4 certainly isn't 21, so that doesn't appear to be the pattern. 3 plus 9 is 12. Aha. And 3 plus 9 is 21, plus 9 is 30. I feel like we're on to it. So what I need to do, based on what my inductive reasoning, is I should add 9, and 39 plus 9 is 48. Now, if I look at my next list, it's certainly not easy multiplication, so I'm going to see if they're adding. So 3 plus 1 is 4, plus 2 is 6, plus 3 is 9. All right, so I'm still seeing a pattern here. So based upon that pattern, I'm going to say we should add 5, and 13 plus 5 is 18. Now, when you deal with fractions, you could look at the entire fraction, but for many, many people, it's easier to think of a fraction as just the ratio of numbers, so that you actually have 2 complete numbers, a numerator and a denominator. And so that's one thing that we can look at here. If you just look at the numerators, what you see here is that on every single one of these, it's exactly the same. So I think that the next one's going to have a 1 on the top for my numerator. Why would that suddenly change? And then looking at the denominators here, I can say, well, 2 plus 4 is 6, plus 4 is 10. Oh, so it looks like we're adding 4 every time. So if I add 4 to my denominator, I'll have a 22. And so a lot of times when you've got fractions, you might want to just take them apart and look at just the numerator and then just the denominator. Now, if I look at this last set, Because I work with math all the time, this kind of screams to me. This is a very special set of numbers, but I don't think students are necessarily going to see that right off. So what can we do to go away that? Well, we might could look at differences, like from 1 to 4, they've added 3. From 4 to 9, they've added 5. 9 to 16 is a difference of 7. And then 16 to 25 is a difference of 9. So if you're looking 3, 5, 7, 9, okay, so the next one would be 11. That works. And so then I need to go up 13 because it looks like we're increasing by odd numbers every time. So if I go up 13, that is going to give me 49. So what is it that I said? That row just kind of screams to me of what's going on here. Here's the other thing. This one is, these are perfect squares. 1 squared, 2 squared, 3 squared is 9, 4 squared is 16. So you can see here, if you just take a number times itself, then we can also find a pattern. Now that nice one is a good example of sometimes there's more than one correct way to get there. What we're trying to do is get there. It's okay if you take a different path than someone else. Okay, so all of those, though, we looked at all those examples and took in some examples to determine what the rule was, and then we applied the rule. This is maybe a little bit blurry, but this is copied directly from the textbook, so you might have a problem like this also, where you're trying to figure out what shape is next. So again, sometimes to take it apart helps. Looking at the top upper area, I have a rectangle, triangle, rectangle, triangle. So that appears to be alternating, and I know I'm not going to draw this very well, but it looks like I should have a rectangle next. Then at the bottom, I have 1 segment, 2, 3, and then 1 segment. So it could have gone up to 4, but it doesn't seem so. It seems like it started over. So I'm going to say my next one should have 2 then. So I'm going to say that that's my next one. Now, yeah, the colors, I didn't get the colors exactly the same. It's the idea. We have another row here where we have circle, square, circle, square. So my next one should be a circle. So that'll be a hoot when I try to draw a circle. Not even looking down. And so we got kind of an egg there. All of these have like an X inside of them. Oh, very bad. So now let's look at the pattern of dots. In all of these figures, I see a section with 1 dot, then 2, and then 3. But the section with 1 dot is not in the same place. It was on the right, top, left, bottom. So if this 1 dot goes right, top, left, bottom, it actually seems to be turning counterclockwise. So from right, top, left, bottom, my next one should actually be back over here at the right again. The 2 is bottom, right, top, left, so it's going to be back at the bottom. So actually what happens is it seems that my very first figure has been repeated. Okay, and maybe I should just kind of draw an arrow there. But I didn't know that at first glance. All right, now this words where it's all typed, this is a different problem, different type of problem. But all of this typed area is like one of your homework problems, essentially. It'll just be different words. So select a number, doesn't tell you, multiply the number by 6, add 8 to the product, divide the sum by 2, and then subtract 4 from the quotient. Repeat this procedure for at least 4 different numbers. So I'm actually going to do that down here. I'm going to pick 1, and then I'm going to multiply that number by 6, and then I'm going to add 8. So 6 plus 8 gives me 14. Then I need to divide that by 2, and that's 7. And now I need to subtract 4. 3. Now I'm going to pick 2. said I could pick any number. Why not pick something I can do the math easily with? So multiply by 6, add 8, divide by 2, subtract 4. If I pick 3 times 6 plus 8, is 26, divided by 2 is 13, and then minus 4 is 9. Okay, one more. The reason we want to do it for at least 4 numbers is because we're trying to establish a pattern, okay? And just like we had on the previous screen where we looked at several different things to get going, you can't really establish your pattern by just the first example. So 4 times 6 is 24, plus 8 is 32, divided by 2 is 16, minus 4 is 12. Okay, so now, just kind of in summary then, I'm going to write this up here in black. I started with 1, and I ended up with 3. When I started with 2, I ended up with 7. I started with 3, my result was 9. And when I started with 4, my result was 12. So write a conjecture that relates the result of this process to the original. It's not just asking me what's happening at the end, because if I look at the end, I might can find a pattern over here, but it's how these numbers relate back to their original. Okay, and now we want to think again, how could these numbers possibly relate to the original? Well, here's what I'm going to do is I'm going to skip down before I write it in words, and this could be because I'm an algebra person and more math oriented, but I'm going to look down here at this last part and see if I can do something with that. No matter what I pick in, I would have to multiply it times 6. So that would be 6n. Then I would have to add 8. And that does not simplify. It's still just 6n plus 8. And then I would have to take all of that and divide it by 2. Now that, I don't know where that straight line came from, but we're going to move on from there. So that's not supposed to be a straight line there. But 6n divided by 2 is 3n. Who knows why my pen is doing this suddenly, and I apologize, but that's 3n. And then 8 divided by 2 is 4. So we have plus 4. So now I'm divided by 2. Now the next thing I'm supposed to do is subtract 4. And I get 3n. Well, now this is very helpful. Because if my original number was n and my result is 3n, now let's go back up and see this. 1 times 3 times 3. You know what this indicates? It actually indicates a math error on the second one. So let's go back and look at the second one. Where did I subtract? Oh, horror of horrors, guys. You all watching this video caught it the moment it happened, but you couldn't scream out to me. But 10 minus 4 is nowhere on this earth does that equal 7. 10 minus 4 is 6. Now, since 10 minus 4 is 6, aha, now the world is better. Every one of those times 3 gives me the result. So what is the process that relates to the original number selected? It is the number times 3. And I could, as a teacher, I could redo this video and erase it and go back. But I think sometimes it's my own opinion that it's worthwhile to see what the process is of working some of these things out. And I don't try to memorize all my answers ahead of time. I work them out so that you can follow that process and see what's going on. But my apologies still yet for making the mistake. Hope you guys will forgive. All right. So we've done all of that type of problem. Let's go to our next one, if I can. Notice down here at the bottom, it has moved to where it says section 2.1. So what we talked about on the conjectures and inductive and deductive reasoning, that's your other example 1.1. And now we move into a new section. So this would be a second set of homework if you wanted to stop it, the video, and watch the rest of it later. So sets are called well-defined when there's no doubt or argument about the members included. So teachers is not well defined. You might think at first glance, well, I know who teachers are, but actually when I said, like if I said all of the teachers, do you mean parents also? Because they certainly teach children a lot. You know, are you only talking about certified educational secondary teachers maybe, or something like that? So we're going to mark this one off and then say teachers at GNTC would be a well-defined set, because at GNTC they actually have a list of people that are teachers as opposed to other roles. The same sort of thing happens here. Presidents is not well defined because you might be the president of a company. But United States presidents is a well-defined list. We can find a list and see exactly who's on it. Now, when you look at sets, even that are well-defined, they may be written as a description or with the roster method. So this is method 1, description. The roster method is the second one, or with set builder notation. So there's 3 ways we can write that. All 3 of these ways are illustrated here below with the same set. So if you wanted to describe this particular set, you could say positive odd numbers less than 10. That's the description. However, the roster actually lists those positive odd numbers less than 10. We've got little braces here, which are curvy on the edges, and we've got 1, 3, 5, 7, and 9. Now this last one is set notation, and it shows that it is between 0 and 10 and that it is odd. So you have to stay between those 2 numbers, and it has to be an odd number. So this is set notation. Now all of these are the same way, but you do occasionally run across some sets that you can't write in the roster method because they're so big you would never get done. So sometimes we just have to use a description or something else along the way. Now this is that last thing that was still there, and it says learn to read it. Whenever you see these arrows, you're supposed to say the set. And then whatever is here, it is of all. So in this case, it's of all x. And this line, which is a vertical line, is generally read such that. So if I wanted to read this mathematically, we would say the set of all x such that. Now here you have a choice. You could read it from left to right. 0 is less than x, which is less than 10. But typically when it's like this, we would say the set of all x such that x is between, as you can see it is between 0 and 10, and, for the comma, and x is odd. So the set of all x such that x is between 0 and 10 and x is odd. Now here we've got some set theory symbols. Some of these come up now, some of them come up in the latter section, and this is unioned. And what I'll do, well, we read this one unioned. And what you want to do with that is look at both sets together. This one is intersected. So A intersected with B. And when you're looking at that one, it has to just be what is in the overlap. What's in both of them. These two are very similar. They both have to do with subsets. It's kind of like the less than symbol that you've used in math that was pointed. If it were a less than symbol, this one would have said A is less than or equal to. And it is very similar to that idea. A is a subset of B, but it could be the same as B. That means all of A is in B. So this one is a, oh, it's so hard for me to write on this thing, subset, okay? And it means that all A is in B, and A might be the same. Might not have, B might not have anything extra. It's kind of like or equal to. But all A is in B, and A might be the same as B. Here, this one is a proper subset. Oh, I left off my S. Subset, and it means that all of A is in B, and B has other things too. And I'm just going to say, and B has more. Because a proper subset then is indicating that they're not equal. B is definitely the bigger one. Now, A is not a subset of B. Does not mean that there's no overlap. But what it means is not all of A is in B. It doesn't mean none of them are in there. They might still intersect, but it does mean that they're not all in there. Now this one just kind of turns it around. And so rather than this, the terminology instead of subset is superset. So our word is superset. But what I'm going to do, rather than rewrite large things out here, it has the same meaning as this one. Based on the previous page, this means that B is all of B is in A, but it might be the same. So that same thing is true over here. This one would be like A contains all of B, but they might be the same. The second one, A is a superset of B, a proper superset, means that B is a proper subset of A. All of B is contained in A, and A has more. So here, A contains all of B and has more. This is the same thing then. To say A is not a superset, we're saying that B is not a subset, which means not all of B is contained in A. So over here, we're going to say A does not contain all of B. Now this one is different. This little C here could be written with just, that's not really supposed to be a 1. It's supposed to be more like an apostrophe or an accent mark. But that means complement. That's the word for it. Now the E in there actually comes from the word complete. So if you had a large set of numbers and then A was part of that, the complement would be the rest of it, because it would be the part that you had to put with A to make it complete. So what this really does in words, I'll try to write this one out, the complement of A is all of the elements or all of the things not in A. Okay, all of the items not in A. Now you can find these again in that online textbook, so if you have trouble getting to it, let me know. But you can also do a Google search where you actually just do a search for set theory notation. So see up here, this says set theory symbols. So you could do a Google search for probably set theory symbols and find a listing of those all in one place for you. And some people would find that handy to do their homework. Okay, some sets of numbers just have their own symbols because they're so big you never want to list them out. You're not going to use the roster method at all. So here are some of those along the way. So natural or counting numbers, I don't know why that straight line's there again, 1, 2, 3, and they just keep going. So I actually did use the roster method, but I also used this ellipsis to indicate that I'm skipping numbers. Okay? Now integers, on the other hand, they don't include fractions or decimals, but they do include negatives, so I can't list them all out, but we're going to say like -2, -1, 0, 1, 2, and then our list just keeps going the other direction. So no fractions, no decimals, but they do include some negatives. Now, rational numbers include all of the integers, and the integers, by the way, include all of the counting numbers. But rational numbers also include, so I'm going to say that this is my Z list and fractions and decimals. I have given up on that little straight line. But fractions may be written as decimals, or decimals may be written as fractions. But here's the thing. Decimals, if you're looking at rational numbers, the decimals have to repeat, like 1/3 is 0.333333, or they have to, the math term for it is terminate, but I certainly don't want to write all that down, so, or they have to end. So like this one could be 0.3 bar, or it could be 0.25. All right, so if it's a decimal, it has to be a repeating decimal or an ending decimal. Now, real numbers include all of the numbers that we ever work with outside of algebra. They include all of the natural numbers, which is all of the integers are included, all of the rational numbers, but they also pick up the decimals that don't repeat and don't end, like pi. So real numbers include all of Q and the rest of the decimals. Now the rest of the decimals, the math term for that is really irrational numbers. But in other words, I could put an example here of pi because of 3.14159, blah, 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 and it just keeps going. Now, I am sorry about the repetition on here because you certainly don't need the natural numbers on there again. That one does come up a lot, but I didn't need to come up twice on this page. So that is repetition. Complex numbers are not something we're really going to be dealing with a lot in this course, but complex numbers include the real numbers plus the imaginary numbers, and I'm not going to say anything else about them right now because I don't think you need them on this assignment, but they're out there. Okay, Now, equal sets and equivalent sets and the cardinality of a set, empty set, okay? Equal sets, in many, many cases, equal and equivalent mean the exact same thing, but they don't in set theory. When you're talking about sets of numbers, equal sets have to have the exact same elements. So if I said that set A had the numbers 1, 3, and 26, and set B had 3, 26, and 1, then equal is my term here. Equivalent sets do not have to be equal. Equivalent sets have the same number of elements. And that number of elements is called the cardinality of the set. So if I have A has 1, 3, and 26, and set B has 2, 5, and 10, now A does not equal B because they are not the same. However, the cardinality is the same. We indicate that, but we do the number of A is 3. That means how many elements are in there. And the number of B is 3. So we would say that A is equivalent to B. A is equivalent to B, B is equivalent to A, but they're not the same. Empty set, the symbol is really the key thing you need to know. It is like a 0 with a slash through it, or an opening brace, and then a closing brace. There is literally nothing listed there. The cardinality of the empty set is 0, but 0 is not an element of the empty set. By the way, I don't think this one was on the previous thing, but I just used the phrase element. Element looks like kind of a C with a line here. And so I could say that 1 is an element of A, and 1 is an element of B. And then down here, 1 is an element of A, but 1 is not an element of B. Now, you're going to have several different lessons about sets, whereas with the inductive deductive reasoning, we pretty much do the one lesson on it, but there will be several about these sets, so do make a note of those symbols. And please don't forget to use the Ask the Instructor and answer your discussion questions. Bye.